Okay, so here is the first theorem of Han-Banach, the geometric version. Okay, so let V be a real non-linear space. A and B, two non-empty disjoint convex sets in V. Let A be open. Then there exists F in B star and alpha in R such that for all x in A and for all y in B, we have fx is less than or equal to alpha less than or equal to f of y. So f equals alpha is a closed hyperplane and it separates the two convex sets. That is what we mean. We have two convex sets A and B, and then you have their disjoint, and you can find a hyperplane f equal to alpha which separates the two. So this is A and this is B. Okay, so this is the kind of theorem which you are going to do. Okay, so proof. So you take C equals A minus B. So what is this? This is the algebraic difference, as I said. So this is all set of all x minus y, x in A and y in B. So it is immediate to see that C is convex. It's no trouble at all. Take any two points, then take a convex combination. It will continue to be here because A is convex and B is also convex. And also this can be written as union y in B of A minus y. So you translate A by y. So that means open set remains open, and then arbitrary union of open sets is open, and therefore C is open. Finally, A intersection B is empty. They are disjoint sets. So this implies that 0 is not in C, because you can't have x equals y. Okay. So now we go to the previous proposition. We have a convex open set and we have a point which is not in it. So it implies there exists an F in B star such that for all elements Z in C, you have f of z is strictly less than f of 0, which is 0. That is, for all x in A, for all y in B, f of x minus y is 0, so that is f of x is less than f of y. So you let alpha equals alpha to be, so choose alpha such that sup f of x, x in A, which will always be less than or equal to inf f of y, y in B, because of this relationship here. So you choose alpha to be between the two, and this may not be a strict inequality. That's why if the two sets touch, then this is what you have. So let us take an example. For instance, in R2, suppose I have the set, take this rectangular hyperbola. So you take y bigger than or equal to 1 by x. So that is one set, and then the other set is y less than 0 or less than or equal to 0. So that is the lower half plane. So this is one convex set. this is the other non-empty convex set, and you want to put a hyperplane between them. So in fact you will see that y equal to 0 is in fact the hyperplane which separates these two. You can't have a strict separation because these two sets asymptotically, though they are disjoint, the points become closer and closer to each other, so they can't be separated by any single plane. Okay, so now we would like to see when you can do a strict separation. So that is the next Hanbanak. So V real non-linear space, A and B non-empty disjoint convex sets. A is closed and B is compact. Okay, so then there exists an F in B star, alpha in R, and an epsilon strictly positive, such that Fx for every x in A and for every y in B, you have Fx is less or equal to alpha minus epsilon, and Fy is greater or equal to alpha plus epsilon. So you see they are away from alpha on both sides, and therefore you say that the hyperplane which is of course closed, the closed hyperplane f equal to alpha strictly separates A and B. So both of them are closed and one of them is compact, then you can achieve the. So in the previous example neither set was compact. You could have made one of them was closed, you could have taken the other also closed if you like, if you took y less than or equal to 0, but they are not compact, and that is why we could not separate them. Okay, so proof. You let eta to be positive, then you take B0 eta is the open ball, center 0, radius eta positive. Okay, and you then take A plus B0 eta and B plus B0 eta. Okay, now because just as I said, this can be, both these sets are therefore open and convex. Convex because each is the sum of two convex sets, and open because B0 eta is open, and just like last time you can write, for instance, A plus B0 eta is B0 eta plus x union over all x in A, and so translation of open set is open, union of open sets is open, and therefore this will be open, and similarly this is also open. So you have your thing. So if eta is sufficiently small, then they are disjoint as well. Why? So because what do? If not, there exists eta n going to 0, xn in A and yn in B, okay, and xn, norm of xn minus yn is less than or equal to 2 eta n, because you will have a common element between these two, and that is xn in A plus something and yn in B plus the same thing. So xn minus yn will be norm less than twice the same thing, and that is less than twice eta n. So that is why you have this thing. So you have, therefore, since B compact, there exists a convergent subsequence. So you have a subsequence y and k converging to y. But xn and yn must converge to the same limit because they are less than 2 eta n, which goes to 0. So this implies that xn k also converges to y. But this belongs to B and A is closed, and therefore this belongs to A. So y belongs to A intersection B, and that is a contradiction because A and B are disjoint. So if you take eta sufficiently small, you can also ensure that they are disjoint. So you have two disjoint convex open sets which are non-empty. So by the preceding theorem, there exists a closed hyperplane, so f in B star alpha in R, such that for all x in A, for all y in B, and for all z1, z2 in the unit ball, such that closed unit ball, that means norm z1, z2 are all less than or equal to 1, f of x plus eta by 2 z1. Now this is in the form x plus b0 eta. So this is an element whose norm is eta by 2, so strictly less than eta. So this belongs to a plus b0 eta, and then that is less than or equal to alpha, which is less than or equal to f of y plus eta by 2 z2. And you can take this for all z1 and z2. So now, this is f of x plus eta by 2 f of z1. Now z1 I can take anything in the closed unit ball, so I take it so that it is close to the supremum, and therefore I will get norm f, because norm f is nothing but supremum of fz, norm z less than or equal to 1. So I can take any z, a sequence for instance, converging to the supremum, so that you will get this. Similarly, this is less than or equal to f, this is less than or equal to fy. Now I take z2 going to the supremum and then take minus of that, so this will give you minus eta by 2 norm f. So now the theorem is proved, so you take epsilon equal to eta by 2 norm f, and that will prove the theorem. So okay, so this proves the theorem, the strict separation theorem completely. So if for instance, if you had the same set, this is y greater than or equal to 1 by x, so this is the upper part of the rectangular hyperbola including that curve, and then you take a small ball center origin here so that they are disjoint, then of course you can find a plane separating the two. All you have to do is take the closest distance here and then take half the distance of that, and that plane will strictly separate the two sets. So this is an example of that thing. So now we are going to have a corollary of this, which is so important. This is probably the most often applied version of the Hahn-Banach theorem. This is how the Hahn-Banach theorem gets applied most of the time. So it's a really very important corollary. So V, real norm linear space, and W, a subspace of V such that W closure is properly contained in V. Then there exists a F in V star such that F is not identically 0, but F restricted to W is identically 0. Okay, so now let us prove this. Okay, so proof. I will come back to the statement and explain how this is a very useful statement. So let us first prove the statement. So let x naught belong to V minus W bar. It's in V but not in W bar. So W bar is closed convex. It's a subspace and therefore it is closed. It's a closure, so it's closed, and it's a subspace, so it's convex. And x naught singleton is compact, and it's a singleton, so it is trivially convex. So there exists a f in V star. I am not worrying about the alpha and the I am not worrying about the epsilon now. So we have that f of x is strictly less than alpha, and it is less than f of x naught for all x in W bar. Okay, so 0 belongs to W bar. So if you put 0 here, so this means that alpha is strictly positive. This means f of x naught is bigger than alpha, which is bigger than 0. So this implies that f is not identically 0. On the other hand, if x belongs to W, then we have nx belongs to W for all n natural numbers. Okay, so we have f of nx is less than alpha, and therefore this means that f of x is less than alpha by n. So you let n tend to infinity. This implies that f of x is less than or equal to 0 for all x in W. But then minus x is also in W, so f of minus x is also less than or equal to 0, and so this implies that f of x equal to 0 for all x in W. So how do we, so this completes the proof. So how do we use this thing? So how do you use this? So to show a subspace is dense in V, that is W closure equal to V. So this is what we want to show. So assume f is in V star, f restricted W equal to 0. Prove that f is identically 0. So this is the way we use, because if f is not identically 0, then you know, if W bar is not equal to V, you know, you can always find a f which is not identically 0. But if you take f vanishing on W and show that it implies that f vanishes everywhere, that will prove that the subspace is dense. So this is how we prove the density of subspaces. So a couple of remarks. So remark 1. So V is a non-linear space over C. Then you know that linear functionals are essentially given by their real part, and therefore conclusions of HB work for real part of F. So because you can consider V as a real non-linear space and real F, and therefore you can say the whole thing. So in particular, above corollary also true for complex non-linear spaces. So this is one condition, and we will give another proof in the exercises using the extension form of the theorem. Okay, so we will do that. Okay, the second remark, in all the proofs we used the fact that there exists a neighborhood of every point which is a ball. And in fact, more than it is a ball, we use the fact that the set which is convex, ball is convex. That is all that we needed. We used the convexity of the ball. For instance, A plus B0 eta, B plus B0 eta were all convex sets, and that is because the ball itself is convex. So this theorem, so we say that a topological vector space V is locally convex if every point has a local basis made of convex sets. Non-linear spaces are trivially locally convex because the neighborhoods are all balls, balls are all convex sets, and therefore, so if you have this, then Horn-Banach theorems true in locally convex topological vector spaces. Okay, so I will stop here with this, and as an application of the Horn-Banach theorem thing, we will study next what is meant by vector valued integration. So if you have a function from the real line into a vector space, we want to give a meaning to the integral, and that is the thing which we will see next.